Okay, in the last class we have discussed about the memory interfacing to 8086. Next, in order to interface the I/O devices, we need a peripheral chip called Programmable Peripheral Interface 8255. Programmable Peripheral Interface. PPI. The IC number of this one is 8255. So, using this 8255, we can connect any input-output device to the microprocessor. Okay. So, 8255 is basically 40-pin IC with the 3 ports called port A, port B and port C. So, each port can be programmed as input or output ports, because we can use input device as well as output device to communicate with microprocessor. And here this can operate in 3 different modes called mode 0, mode 1, mode 2. Port A can operate in all the 3 modes, port B and port C can operate in only 2 modes. Okay. So, the detailed pin diagram of this one and the architectural diagram of this one, so we will discuss in the next slide. So, if you take the block diagram of this 8255, as I have told, there are 3 ports, which is port A, port B and port C. But port C is again divided into 2 sub ports, they are called port C upper and port C lower. So, this port C upper is PC7 to PC4, port C lower is PC3 to PC0. Okay. So, these two are called group A, and these two are called group B. Okay. And there will be some data buffer, we will be having 8-bit data bus, and then we have read bar signal, write bar signal, A1, A0, which are used for selecting these ports. There is one reset signal, chip select bar signal. To select this particular chip, we require chip select signal, and we require plus 5 volts and ground to operate this IC. Okay. So, here this is read write logic. Using this read write logic, we can select the type of operation, whether it can be reading from the input device or writing into the output device. This A1, A0 is going to find out there is a control word register. Inside this read write logic, there is a control word register which plays an important role. CWR. CWR stands for control word register. By programming this control word register, we can program the ports as input or output port, and in any one of the modes, mode 0, mode 1 and mode 2. Okay. So, this A1, A0 is going to decide A1, A0. If they are 0, 0, then the control word referred to port A. This is 0, 1, port B, 1, 0, port C, 1, 1, control word register. See how A1, A0 will be used for selecting the ports or control word register. Okay. So, the format of this control word register is 8-bit register. This is 8-bit register. The format of this control word register is as follows. This is the format of the control word register. So, we have this D0 LSB bit, which will be used as a port C. So, you can program this port C lower, which is PC3 to PC0 as either input port or output port. If this bit, if you make as 1, this will act as input port. If I make as 0, this will act as output port. The next pin will be for selection of port B. Again same thing, 1 means input port, 0 means output port. So, the next bit will be mode selection of this port B, mode selection of port B. So, port B can operate in only two modes. Port B can be operated in either mode 0 or mode 1. Whereas port C can be operated in only one mode, which is mode 0. So, there is no bit to select the mode of port C, because only by implied it is mode 0. Okay. Whereas port B can operate in mode 0 and mode 1. So, we have one bit for selecting this mode 0 or mode 1. Then coming for the group A signals, port C upper, this is by default mode 0, 1 means input, 0 means output. Port A, again we can program this port A as either input port or output port by selecting 1 or 0, by placing 1 or 0 into corresponding bit position. But port A can operate in 3 modes: mode 0, mode 1 or mode 2. That is why we require at least 2 pins to select the mode of this port A. So, here we have used this D4, D5 and D6 for selection of the mode. 0, 0 is mode 0, 0, 1 is mode 1. Either this can be 1, 0 or 1, 1 is mode 2. 1 X means X is you do not care, which can be either 0 or 1. Then coming for the MSB bit D7. So, this 8255 can operate in 2 modes, overall this 8255, which is called IO mode or BSR mode. This is sometimes also called as control word mode, CD mode, control word mode or BSR mode. BSR stands for bit set reset. So, in IO mode or CD mode, we cannot program the single bit of a port as a input port or output port. The entire port can be programmed as either input port or output port. It is not possible to program a bit of port as input port, a bit of the same port as output port and all. Whereas in case of bits reset mode, as the name implies, so one pin of this port A, so the port A will be having 8 bit pins, PA7 to PA0 is port A. In case of IO mode, so the mode selection for port A is this D4 bit. If D4 is 0, the entire port A will be programmed as output port. If this is 1, the entire port A will be programmed as input port. We cannot program PA0 as input, PA1 as output and so on. Okay. But this is possible. PA0 you can program as some input port, PA1 you can program as output port in case of BSR mode, as the name implies bit set reset mode. So, that is the difference between the IO mode and BSR mode. In case of IO mode, we can program the entire port as either input or output port, whereas in bit set reset, each bit of this port can be programmed as either input or output modes. Okay. So, that is about this control word register. So, depending upon this control word register, the 8255 will program the ports as either input or output ports and any of the modes, mode 0, mode 1 and mode 2. Okay. So, now using this 8255, we can connect any input output devices. First, I will take a simple example of connecting a LED, light emitting diode, a simple output device. Before that, I will discuss the interfacing of 8255 to 8086. So, what are the connections required between these? Okay. So, we know that 8255 we have discussed the pin diagram. So the different pins of 8255 are, we have 3 ports. This is PA7 to PA0 is port A. Then we have port B, PB7 to PB0, and port C is available as port C upper as well as port C lower. All these are bidirectional because they can be programmed as input or output ports. This is called port C lower. And then we have PC7 to PC4, port C upper, port C upper. This is 8255. And in addition to this, we have read bar signal, write bar signal. Then we have chip select bar signal. Chip select is active low signal. Then we have A1, A0. So this A1, A0 has to be connected to the A1, A0 of 8086. Okay. So here this port can be either 8-bit port or 16-bit port. So this you have to connect to A1 and A0 of 8086. These two corresponding read and write bars of microprocessor 8086. Reset also you have to connect. The only thing is how to generate this chip select signal for this 8255. So here we have 8086. This is 8086. You simply connect these two, A1 of 8086, this you connect to A0 of 8086. This you connect to read bar of 8086, write bar of 8086. Now how to find out this chip select signal? Okay. So here we have totally 20-bit address lines, A19 to A0. Out of this A0, A1 I have connected to this A1, A0 of 8255. I will use this port addresses as only 8-bit. You can use 16-bit also. So in that case I will use only lower order 8 bits of this address bus. So what is the lower order 8 bits of the address bus? A7, A6, A5, A4, A3, A2, A1 and A0. Anyhow, we are going to connect to A1, A0 of the 8255. As I have discussed, the function of A1 and A0 of 8255 is zero zero. It will select port A. 01 port B, 10 port C, 11 control word register. This is the selection. Here this A1, A0 I am going to connect to here. Suppose if I make this remaining A2 to A7 as all ones, it is up to you, can connect to either zeros or ones. Here I am assuming that they are connected to 1. Okay. Then what is the address of port A? If A1, A0 is 0, 0, then port A will be selected. So what is the 8-bit address? This will be C, this will be F. So this address will be FCH. And if I want to select port B, this I am going to fix for all the ports as all ones. All ones. Now what is different is A1, A0. For 0 0 you are getting FC address, so this will be the address of port A. And for this 0 1, what will be the corresponding hexadecimal FDH? This F is 4 ones and 1101 is 13D, and this is for 10, this will be FEH. For 11 this will be FFH. So the address of this port A becomes FCH, this will be FDH, this will be FEH, and this will be FFH. Okay. Now how to select this chip select signal? So you have to connect this A2 to A7. So I am taking A2 to A7 of this microprocessor, A2, A3, A4, A5, A6, A7. If all are ones, this chip select should be 0. This should be 0 to select the chip. So if A2 to A7 all ones, then the output of the gate should be 0. So which gate you have to use here? Is NAND gate. You connect the output of this NAND gate to the chip select of this. This is A2, A3, A4, A5, A6, A7. If all are ones, for the NAND gate, if all inputs are ones, then only output is equal to 0. If any one of the input is 0, output is 1. Okay. So only for these particular 4 combinations only output of the NAND gate becomes 0, thereby this chip will be selected. After selecting this chip, this A1 and A0 is going to decide within this 8255 we are going to select the port A or port B or port C or controller register which is stored here. Now with this interfacing diagram, the address of the port A is FCH, port B is FDH, port C is FEH, and control register is FFH. Okay. Suppose if I want to connect in any address locations, then accordingly you have to set these connections. This is how we can connect this 8086 to 8255. Okay. So I will discuss about how to connect this 8086 to 8255 for a given address locations. Suppose you will be given to interface (8255) to 8086 to meet the following specifications. For example, if I want port A as, it's up to you, you can take any 4 consecutive locations, 00H, port B as 01H, port C as 02H, control register as 03H. So this should be consecutive locations. Then what will be the connection diagram? This is similar to this earlier one, except for that it depends upon the address map, you have to select the chip select signal. So this is 8255, 8086. Remaining all connections are same, A1 to A1, A0 to A0. I am going to just show how the chip select will be generated. So what is the address map for port A? A7, A6, A5, A4, A3, A2, A1 and A0. So what is 00H is equivalent to 00000000. So what is 01H? 00000001. 02H? 00000010H. 03H? 00000011H. You see here, for all these combinations, this A2 to A7 all are zeros, whereas A1 A0 changes. This is for port A 00, port B 01, port C 10, control word 11. Anyhow, I have connected this A1 A0 to A1 A0, so that will select the ports and the control word register accordingly. Now using this address lanes of this 8086, so if I want to interface in this address, so what should be the hardware required to select this chip select of 8255 is, so whenever these all are zeros, then the output should be 0. If any one of the input is 1, output should be 1. So what is the gate? So you take this A2 to A7, connect to a gate A2, A3, A4, A5, A6, A7. You choose a gate such that whenever all the inputs A2 to A7 are 0, output should be 0. If any one of the input is 1, output should be 1. Okay. So what is that gate? OR gate, right? So for OR gate, if all the inputs are 0, output is 0. If any one of the input is 1, output is 1. Okay. So this is how you can connect 8255 in a given locations, or for a given connections we can find out what are the address of port A, port B, port C and control register. Okay. So this is how we can connect 8086 and 8255. Now assuming these connections, then how to connect a LED? First of all, what is the need of this? If I want to connect a LED here, why don't you connect LED directly to 8086 or input device such as keyboard or 7 segment display? So these devices, why don't you connect directly to the 8086 without using 8255, without using this 8255? The reason is this, input output devices operates on some electrical characteristics, whereas 8086 will operate with some other characteristics. Okay, because of that there will be some mismatch. Okay. So in order to match the electrical characteristics of 8086 with input output devices, we need interfacing circuitry such as 8255. Okay. Now let us take a simple example. Interface LED light emitting diode to 8086 and blink at a rate of some 1000 microseconds. Okay. So this 8086 and 8255 connections I have already discussed. This is 8086. So I am going to program this LED through 8086 only, but we are going to connect interfacing device in between. So the connection between these I am not showing. How to select port A, port B, port C and all, that I have already shown in the earlier slides. Okay. Let us assume that the connections are such that the port A address is, you can choose any addresses but consecutive addresses. You take same this first example FD, port B FE, port C this is FCDEH, FCFD, FCH, FDH, FEH and control register FFH. Then in order to connect a LED, this is an LED, light emitting diode. If the anode operates at 5 volts, cathode is grounded, this will emit the light. This is the symbol of ordinary diode. If I add this light symbol, then this will be LED. So I am going to ground the cathode. If I give 5 volts here, LED will glow. 5 volts means logic 1. If I give 5 volts or logic 1 here, implies LED will glow. If I give logic 0 here, which is equal to 0 volts, LED will be off. Then in order to connect this, we know that 8255 is having 3 ports, port A, port B, port C, and inside this we have of course control over register. So I need only one port bit, okay. So you can connect to any port. Suppose if I want to connect this to PA0 of port A, I have this entire port A, this is port A. So in that we have PA0 to PA1, PA2, PA3, PA4, PA5, PA6, PA7. But only one port pin will be enough. So I am connected to PA0. Okay. I am not using port B and port C, I have not shown here. You can use pin of port B as well as port C also. Okay. So for these connections, so I want to blink this LED at a rate of 1000 microseconds. It should be on for 1000 microseconds, on for 1000 microseconds, then off for 1000 microseconds, and we have to repeat the same thing. Okay. For that very first step, in order to connect any input output devices, you have to set this control over register to meet the requirements. So what is the requirement here? Out of the 3 ports we are using port A only, but in port A also I am using single bit, so you can use bit set reset mode also. Okay. And if you want to use IO mode, so you have to set this port A as output port. And which mode? We take simple mode 0. So I will discuss the different modes, what are the things in different modes. So I will take simple mode 0, which is called as simple IO mode. Any port can be programmed as either input or output mode. And what about port B, port C? I do not care. Port B, port C can be either input ports or output ports, and port B can operate in either mode 0 or mode 1. Okay. I am not interested in those ports because I am not using those ports. Okay. Then what will be control over register? I am using this in IO mode. So this D7 pin, D6, D5, D4, D3, D2, D1 and D0. So this D7 should be 1 for IO mode. If it is bit set reset mode, this will be 0. Okay. So in this D0, this stands for port C lower. This stands for port C lower, as I have discussed in the earlier slides. So I am not using port C lower, so I can program this as in either input mode or output mode. So for the sake of simplicity, I am representing this as output mode. This is port B. Port B also I am not using, so I can use either 0 or 1. So I am using 0 means port B also will act as output port. This is mode selection, I want to operate in mode 0. And this is port C upper, I am going to program as output mode. And what about D4 bit? This is for port A. Because I am using only port A, this is important. I have to set this as 0 for output mode, 1 for input mode. Because I am using this port A as output port, I have to set this as 0. So the remaining last 4 bits can be either 0 or 1. whereas this should be 0, and these 2 bits are for mode selection of port A. So I am using mode 0, means this will be 0 0. So I am using 0 0. So what is the control word now? This is 8 and this is 0, 80 hexadecimal. So if I place this 80H into this control word register according to this control word format, this will set all the ports as output ports in mode 0 and in IO mode. Okay. So this is the first step. We have to find out what is the control word register required. Then you can write the program. Okay. So in order to write the program, so I have discussed 2 instructions called in and out instructions. This in and out instructions are used for reading and writing the data from the ports. Okay. So first of all, you take this move data segment register with some address, so the same as that of the other instruction that I have written, move data segment AX. Now for in and out instructions, so you have to output the data. So you take some data into AL register. So we know that there are 2 instructions, in and out. Out instruction is nothing but out port address comma AL. This will output the data from the AL onto the port address that is specified in the instruction. Okay. Similarly, you can have, if it is 16-bit data, we can have out port address comma AX. But here we are assuming only 8-bit of the port addresses. So first I have to set the controller register, I have to load with 80H. Okay. So whatever the data that I want to output, first you have to take into AL register by default. Then out AL to which port? What is the port address of controller register? I have assumed that controller register is FF. So this should be FFH. So with these 2 instructions, the 8255 sets all the ports as output ports in mode 0. But I have used only port A. So anyhow port A also will be used as output port. Now what you have to do? Now you have to send a logic 1 on this, so that LED will close. Then you call a delay, then again you send logic 0 here. Okay. Send a logic 1, call delay, then send logic 0, then you repeat the loop. Again you send the logic 1, delay, logic 0. So continuously this LED will blink at a rate which is set by the delay program. Okay. First I want to set one logic 1 on PA0. So what you have to take? Move AL comma 0 1. So what will be the 8-bit of this 01H? 01H is nothing but 0000 0001. Okay. If I write out, what is the address of the port A? Port A address is FCH. I want to output this data onto FCH, port A. So after these 2 instructions, what happens? This port A, this is PA0, this is PA1, and so on up to PA7. So this PA0 becomes 1. PA0 becomes 1. So PA0 is connected to LED, so LED will close. With these 2 instructions we can on the LED. Then I have to call the delay program. I will discuss how to write the delay program after this program. Okay. So this delay, the rate at which you want to blink this LED, that you can set that delay using the subroutine. Then after this delay, what you have to do? You have to make LED off, means PA naught should be 0. So for that you take move AL comma 0 0, then out onto the same port A. So with these two instructions, what happens? PA naught, of course PA1 to PA7 also becomes 0, but I am not interested because I have connected PA naught to the LED. So PA naught becomes 0, which implies LED is off. So one cycle is over, on, then call delay, off. I have to repeat the same thing. You call the same delay again. Then unconditional jump to up. So this up will be at this instruction. So that again AL will be taken as 0 1, it will be outputted onto port A. So LED will be on. After some delay, LED will be off. After some delay, again because this will go here, LED will be on, off. This will be on and off with a rate of the delay that is provided by this subroutine. Okay. This is how you can connect a simple LED to the microprocessor 8086 through 8255, and you can blink the LED. Okay. Now how to find out this delay? Even if I want to generate a square wave, also the same program. Instead of connecting this LED, if I connect to the CRO, because here we are getting 1 for some time, this is 1, logic 1, some delay, then we are making logic 0 with same delay, and then you are repeating this 1 and 0, 1 and 0, which is nothing but square wave. Okay. So instead of this LED, if I replace with CRO, we can observe a square wave on the CRO. And what is the frequency of this CRO? That will be decided by this delay subroutine. Okay. Then how to write the delay program? Okay. So you load some CX with some number, move CX comma some number, this is 16-bit number. You perform some no operation. So basically it does not perform any operation, as I have told while discussing about the instruction set. This simply provides some delay. Then loop up, up will be here. After that, of course, the return instruction will be there, and the last instruction is return. So in case of move instruction, the number of cycles will be 3. Number of clock cycles is 3. The 8086 is designed such that this move instruction requires 4 clock cycles, 4 clock cycles, and NOP each requires 3 clock cycles. This loop up will take 17/5 clock cycles. Okay. So return also it will take some clock cycles, say this is some 10. So if I operate this 8086 can operate at 3 different frequencies. If I use that, 8086 operates at 5 megahertz clock. So what is the period of each clock period? Is equal to 1 by 5 into 10 to the power of 6, which is nothing but 0.2 microseconds. To get a delay of 1000 microseconds, how many clock cycles are required? How many? So, this is 0.2 microseconds per clock cycle. Okay. So, for 1000 microseconds, 1000 divided by 0.2, which is nothing but 5000 clock cycles are required. If this program gives 5000 clock cycles, then this will give a delay of 1000 microseconds. This 1000 microseconds delay is required in the program that I have discussed in the previous slide. Okay. So, this how many times this particular instruction will be executed? This is number of clock cycles, number of times the instruction is executed. Because this move instruction is not there in the loop. So, in the loop we know that, so this loop nothing but it will decrement the Cx, register, it will loop if Cx is not equal to 0. Okay. So, because this is outside the loop, this will be executed only once. And this how many times this will be executed, because n is loaded here. So, this will be executed n times, this also will be n times, this also will be n time, this is also only one time. Okay. So, here this 17 by 5 is whenever it jumps to the loop, 17 cycles are required. Whenever it exceeds, the loop exceeds, then 5 clock cycles are required. So, in the loop, in jump 17 cycles are required, for exit 5 cycles are required. Here how many times this will jump? N minus 1 times it will jump to up, and 1 time exit. Okay. So, then what will be the total delay of this program is number of clock cycles into number of times plus this number of clock cycles into number of times, number of clock cycles into number of times. So, like that you have to add. So, here total clock cycles is equal to 4 into 1 plus 3 into n plus 3 into n, because these 3 instructions in fact will be executed n times, plus out of this n times, n minus 1 times this will be jump to up. So, n minus 1 times 17, or you can write 17 into n minus 1 plus 1 time 1 into 5 plus 1 time 10, if it written is 10. So, this should be equal to, this is total number of clock cycles. If this is equal to 5000, this is equal to 5000, then we will provide a delay of 1000 microseconds. Okay. If I solve this for n, so we will get something like n is equal to some 228 value decimal. So, the corresponding hexadecimal you have to place here. So, what is the hexadecimal equivalent of 228? That value 228 is 16 1 jar 16, 6, 8, 16 4 jar 64, 4. So, this 228 if you want to convert into hexadecimal, 16 14s are 4 is the remainder, 16 zeros, 14 is the remainder. So, 14 is nothing but E, and you have to read from bottom to top. So, this is equal to 0 0 E4 H. By simply replace this n with 00E4H. This will give the delay of approximately 1000 microseconds. If I change this value, the delay amount also will be changes. So, like that we can generate any delays. Okay. So, this is about simple interfacing of a output device which is such as LED or CRO. So, you can generate either square wave of any desired frequency using 8086 and 8255. Similarly, you can blink the LED at any desired rate. Similarly, you can connect a switch also, input device. So, I have discussed about the output device. Now, I want to discuss, or I want to connect input device to the 8086. Interfacing of a switch to 8086. So, we cannot connect this switch or LED directly to the 8086 because of different electrical characteristics. So, we need 8255 in between. So, I am not going to show this 8086 and 8255 connections because that I have already discussed. So, there is 8086 and 8255 will be connected using the interfacing circuitry that I have discussed in the earlier slides. So, the connections are such that I will take the same 8255 control load register. Let the address of this one is FFH and port A is, this is port A, this is PA0, this port A address is FCH, port A, and port B, port C will be having FD and FEH. Here also, because only single switch is there, I need only one port. Okay. So, I am going to connect this port A. This will be programmed as input port. I have a switch. So, this switch have two positions. In one position, this will be connected to ground. In another position, it will be connected to VCC. Okay, this is the diagram. Switch, if I connect to this, this is logic 0. If I connect this switch to this, this is logic 1. Okay. So, I want to read the status of this switch. I have connected this as PA0, I am connected this as input port. Let us write a program. This is interfacing, simple interfacing. Let us write a program that if switch is connected to logic 0, so you do some operation. If switch is connected to logic 1, you do some operation. Okay. Let us assume that, so if switch is connected to logic 0, store 00H in the data segment pointed by 5000H offset. If switch is connected to logic 1, store FFH in the same offset 5000H. That is in the data segment. This is data segment, says 50,000H is the starting address. The offset of 5000 will becomes, this is 55,000, offset is 5000. here I want to store either 0 0 or FF, depends upon whether switch is connected to logic 0 or logic 1. Okay. So, what will be the program for this now? So, if I take the control word, I am using IO or CD mode only. So, MSB bit should be 1. Okay. And what about the LSB? I am not using port C upper or port C lower. So, simply this is a do not care. So, I will take for the sake of simplicity 0. This is also do not care because I am not using port B at all. So, I will just for the sake of simplicity I will take 0. This is for mode selection of port B. So, this also I want to operate in mode 0. These three are in fact do not cares. Then port C upper, this also I want to program as output mode. These actually in fact are do not cares because we are not using these ports. For the sake of simplicity I have taken as zeros. Then what is important is here the remaining 3 bits. This is for port A. 1 means input port, 0 means output port. Because you are using this port A as input port, so this should be 1. And if I want to operate this in mode 0, this will be 0 0. So, what is the control load register? This is 1000 is 90H. So, initially you have to load this 90H onto, if I read the program, so the first 2 instructions are say move AX comma 5000 starting of the code segment, then move DS comma AX, and the offset is 5000 that you can point to. You can take LEA, BX also you can take, SA also you can take, say BX 5000 because offset is also 5000. Then move AL comma 90H. First I have to set the controller register. This I have to output to controller register whose address is FFH comma AL. So, with these 2 instructions it will set port A as input port, port B, port C as output port in mode 0, but we are not using port B and port C. So, this will set port A as input port, port B and port C as output ports. In all mode 0, all will be operated in mode 0. Okay. Here we are interested in only this port A port only. Then I have to read this. Okay. To read this, what is the instruction? In AL comma, from which port this switch is connected? To port A whose address is FCH. So, FCH. So, here whatever the data 8-bit data. So, this remaining 7 bits are do not cares, we are not using anything. This only the PA0 bit is having the original information of this switch, whether this can be logic 0 or logic 1 depends upon whether the switch is connected to this position or this position. Okay. So, here in order to check the last bit without affecting the other bits can be either 0 or 1, we do not know. Okay. So, with this the status of the switch also will be present in the last bit of AL. This is the status of switch. If this is 0 means switch is connected to 0, this is 1 means switch is connected to 1. The remaining all 7 bits are do not cares. So, I will just make this one as all zeros. For that I am ending end AL comma 0 1. So, this data whatever is the data you are ending with 0 0 0 0 0 0 0 1. So, what happens? This bit remains same, whereas the remaining all bit becomes zeros. Okay. After this ending operation, if the result in AL is 0 means the switch position is 0. If the result in AL is non-zero, because the remaining 7 bits are zeros, means the switch is connected to logic 1. Okay. After ending this one, jump not carry, no carry means the result of the operation is, or you can write the jump not 0 also, because the result can be either 0 or non-zero. Jump not 0, not 0 mean the sense what happens, AL contents are not 0 means AL contents are 1, only have two possibilities either 0 or 1. AL contents is 1 means switch is connected to this plus 5 volts. So, if switch is connected to plus 5 volts, I want to store FF into 5000H, okay, down. Otherwise, so I will write here down, I have to store FFH into 5000H, okay. For that you take some move BL comma FF and move contents of SI comma BL, so that FF will be stored in the location whose offset is 5000H. If this is true, if this is false means I have to store 0 0. So, for that you have to take move BL comma 0 0, then move SI comma BL. So, in any case we have to halt, either the program can be halted here or program can be halted here. If want to check only once, if want to check continuously, then instead of this halt you can write unconditional jump, you can write unconditional jump to up. Here also you can write unconditional jump to up, this up will be here, so that it will continuously check the status of switch. Okay. This is how we can connect a simple switch which is called input device to the microprocessor, a simple output device such as LED to the microprocessor. This will be possible through 8255, the programmable peripheral interface. Okay. Later we will move on to the some complicated input output devices such as 7-segment display, keyboard. These things we will discuss in the next class. Thank you.